Okay, so first thing I'm going to do is figure out the one current. There's just one current, and it goes through that ammeter, through that resistor, through this resistor, through that resistor, through this ammeter, through that resistor, back to the pump. Okay, so the current is just going to be the voltage divided by the total resistance, right? So it's going to be 45 volts divided by, well, let's do it, 4.1 plus 5.4 plus 6.3 plus 4.7. Okay. I think that's it. 1, 2, 3, 4. Did we get them all right? Yeah, I always double check. Because you get this wrong and every other answer is wrong. Okay, so alpha F1, enter 45 in the numerator and 4.1 plus 5.4 plus 6.3 plus 4.7. 6.3, 4.7. All right, confidence. This is 2.19512. Okay, so this ammeter here is going to read 2.20 amps if we round that to 3 sig figs. And this guy here is also going to read 2.20 amps because it's the same current. Remember, the electrons aren't used up. It's just like they just shuffle along the tube. They lose pressure, but they don't get used up themselves. And this is literally how many coulombs per second of stuff that's going by. Okay, so we're good there. Let's see. We've answered those questions. And then we got to figure out the voltmeters, right? So let's do V1. Well, V1's complicated, right? We're going to do IR. But notice that there's two resistors in there. So we're going to add them both together for our resistance. So that's 2.19512 times, and then if we go from the upstream side to the downstream side, we have 4.1 and 5.4. So let's figure that out. So that guy times parentheses 4.1 plus 5.4. That's 20.853, which is about 20.9 volts. Okay, let's look at V2. Ooh, V2 is mean too. Oh my gosh, this is not nice. IR, so that's going to be 2.19512 times, okay, so V2, we're going to start on the upstream side and add up all the resistors. So 6.3 plus the ammeter is 0 plus 4.7. And now we're back to the other lead, right? So that guy times parentheses 6.3 plus 4.7 is 24.146, which is about 24.1 volts in the land of 3 significant figures. And look at V. V3 is really trying hard to look like, I could have, by the way, connected V3 right here. And it would be simple to be like, oh, it's around that. But it's around the ammeter, which has 0 resistance, so it doesn't matter, and the 4.7. Okay, so V3 is IR is 2.19512 times, and let's go from the upstream side to the downstream side, right? So first thing we encounter is the ammeter, that's 0. Then the 4.7, and now we're back to the other lead, right? Okay, so what is that? 2.19 whatever times parentheses 0 plus 4.7. My calculator is probably going, why did you add 0? That is 10.317, or about 10.3 volts. Now it says, what is the greatest power dissipated by a resistor? My suggestion for these types of problems, for series ones, the ones you're not joking about, right? We have a series problem here. Okay, is that you use power is I squared R. Okay, because you always know the current. That's the first thing we figure out. That's our I. And then we also know all the resistors, right? And this helps you figure out which one's the greatest power, right? If it's I squared R and I is the same for all these resistors, then it must be the case that the largest resistor gives us the greatest power and the smallest, okay? So which one's our greatest resistor? I think the 6.3 ohm is, right? So power is, and the reason there's more power dissipated at that resistor is that it's the same amount of current, but it's got to push harder to get through that one. So it's going to dissipate the most energy doing so, okay? So I squared, it's 2.1912 squared times 6.3. So let's grab that guy squared times 30.356 watts, or about 30.4 watts. Now, if you get the test, you're like, oh, I don't know which one is the greatest. Well, find the smallest resistor, figure out the power. Find the largest resistor, figure out the power. And one's bigger and the other's smaller, and so you answer the question. All right.